In this video, we're going to explore Hess's law and how we can apply that to thermochemical equations. Hess's law tells us that if a reaction is carried out in a series of steps, then delta H for that reaction will be equal to the sum of the enthalpy changes for each of the individual steps. This comes in helpful for us if we're interested in studying the enthalpy for reactions in which we cannot measure the enthalpy directly. For example, if we want to study the enthalpy of the reaction of carbon and oxygen to form carbon monoxide, we run into a problem because the carbon monoxide will almost immediately react with O2 to then go on to form carbon dioxide. This makes it nearly impossible for us to directly measure the enthalpy for the formation of carbon monoxide. In order to do this, though, we can use two equations in which we can measure the enthalpy from. We have carbon monoxide plus oxygen to form carbon dioxide. We can also take our carbon plus oxygen forming carbon dioxide. We can measure the enthalpy fairly easily of these two reactions. And so this is all of our given information. So in this problem, again, we want to actually measure the enthalpy of this reaction here. We cannot measure that enthalpy directly, and so we will instead use what we know about two different reactions in order to get us there. When we're looking at Hess's law, we have to keep in mind that delta H is a state function, which means that it doesn't matter what pathway we take to get there, as long as our products and reactants are the same, then the delta H will be the same. What this means is that if we can find a way to calculate the energy in this pathway, going from carbon to carbon dioxide to carbon monoxide, it will equal the energy of going directly from carbon to carbon monoxide. Let's take a look at an energy diagram to get an idea for how Hess's law is applied. And so we're interested in the reaction between carbon and oxygen to form carbon monoxide, but we cannot measure that energy change directly. However, we do have enthalpy information for the reaction of carbon plus oxygen to form carbon dioxide. We also have enthalpy information for carbon plus oxygen to form carbon dioxide. And so remember, as a state function, the quantity of heat of this reaction is independent on the pathway. And so what that means is that we can use the energy we know from this reaction and then the energy we know from this reaction in order to get there. And so we know that this reaction releases 393.5 kilojoules of energy. We also know that this reaction releases 283 kilojoules of energy. And so that means that the opposite direction will require an input of 283 kilojoules of energy. And so we release 393.5. We have to input another 283 in order to get back up here, which leaves us with an energy release of 110.5 kilojoules. So again, that was 393 released to get to here, but then an input of 283 to get back up to our products of interest, for a total energy release of negative 110.5. And so the general pathway to completing Hess's law problems is to manipulate the equations in whatever way you need to in order to get products and reactants where you want them to be, add and subtract a reactants and products. Remember that what you do to the reactants and products will affect our delta H value, cancel out what appears on both sides of the equation, and then look to be sure that you have the products and reactants where you need them for your target equation, and then worry about adding up all your numbers last. I know that seems a bit confusing to look at it here, so let's look through a couple examples. So in the example that we just looked at, our target equation is our carbon plus half O2 to give us carbon monoxide. Our given information was carbon monoxide plus half O2 gives us CO2, and we had the energy for that. We also knew that carbon plus O2 gives us CO2. We had the energy associated with that. Now we can see that in our given information, we have carbon monoxide as a reactant. However, we need carbon monoxide as a product. So what we're going to do is reverse this equation in order to get carbon monoxide as a product. Remember, when we reverse an equation, that will reverse the sign of our enthalpy. And so here we have the reverse equation with an opposite sign. I just crossed out the top one because we don't need it anymore. We're now going to work with the opposite equation. And we can see now that we have carbon dioxide as both a reactant and product in our given information. And so we can cancel those. We also have half oxygen as a product and 1 oxygen as a reactant. And so we can cancel out our half oxygen as a product, and that leaves us with a half an oxygen for a reactant. And now let's take a look at what we have left here. So remember that we're looking for carbon plus half oxygen on our reactant side. And we see that that is in fact what we're left with. The only thing on our reactant side is carbon and half an oxygen. We don't have anything left on the reactant side in this equation. In our product side, we're looking for CO. We want carbon monoxide. And we see that that is in fact the only thing that we're left with on the product side in either of our equations. And so we've successfully manipulated our equations in order to attain our desired equation. And so now we simply add up our enthalpies. Positive 283 and negative 393.5. We add those together, and we get our negative 110.5 kilojoules per mole that we found before. In this next example, we want to know how much energy is involved in converting 1 mole of water vapor to 1 mole of liquid water. And so we can see that if we know the enthalpy change of the formation of liquid water from its gaseous elements, if we also know the formation of gaseous water from the gaseous elements, then we can subtract those two in order to find our enthalpy of converting 1 mole of gaseous water to 1 mole of liquid water. Let's look at how we would set that up with our thermochemical equations. And so in our given information, we start first with our reaction of the formation of gaseous water from its elements. Now this is actually a fully balanced equation, and so our delta H for that reaction is double compared to what we saw on the last page, because we're forming 2 water molecules. We also have the formation of liquid water from its gaseous elements, and that associated delta H. And so what we want to calculate is our formation of liquid water from gas. We want that delta H value. And so, like last time, one of the first things that we see is that we need our gaseous water as a reactant, but it's here as a product in our first equation. And so the first thing that we're going to do is flip that equation, and in doing so, we have to flip its sign. And so we no longer need the top equation. We flip that, we're using a different form of it. And now if we take a look at what we have 2 H2O's on our reactant side, and so that's good. We have 2 H2O's on our product side, and then we see that we have 2 H2 as a product here and as a reactant here, so those can cross out. O2 as a reactant, O2 as a product. So the only things we have left are the things that we're looking for. We have our enthalpy values, so we can add those up. And then we can divide by 2 to get down to values for 1 mole, giving us a total enthalpy value for the formation of liquid water from gaseous water of 44.0 kilojoules per mole. Here, we're going to look at a slightly more complicated example that will involve 3 different chemical reactions. We want the enthalpy involved in the formation of methane and carbon dioxide from 2 moles of carbon and 2 moles of water. These are the equations that we have to actually work with, though. And so let's see how we can manipulate those in order to get our given reaction. I would set it up like this to start out. So here's all 3 of our given equations first, with the delta H values. And this is the equation that we're looking for. And so I would set up Hess's law problems exactly like this. Notice that I gave myself some room in here in order to manipulate or change my equations if I need to. So one of the things that we first notice is that we need carbon as a reactant in our final equation. However, we need 2 carbons as a reactant. The only equation with just carbon in it already does have carbon as a reactant, however, it's only 1. So the first thing I'm going to do is double our top equation in order to get 2 carbons as a reactant. Now, since I doubled that equation, I also had to double my delta H value. We also notice that we need methane, CH4, as a product. We only have 1 equation that has methane in it, and it's currently a reactant. So we need to flip that equation in order to get methane as a product, and when we do so, we need to reverse the sign of that delta H value. And so now we have everything that we need on the side of the equation that it needs to be on. Let's take a look at what we can start canceling out. We see that we do have 2 carbon monoxides as a product in our top equation, and we have 1 carbon monoxide in our second equation and 1 in our third as reactants. So those can all cancel out. Next, we also see that we have 1 water as a reactant in our second equation and 1 water as a product in our bottom equation. And so those can cross out. We also see that we have 1, 2, 3 H2s as products and 3 H2s as reactants. And so those can all cross out. And we see that what this leaves us with are our 2 carbons and 2 waters as reactants. And that's what we're looking for, so that's good. We're also left with CH4 and CO2 as products. And so we have successfully manipulated our equations how we need in order to attain our target chemical reaction. And so now we can just sum up our 3 delta H values for a delta H of 14.7 kilojoules for this reaction. And so, again, the basic steps in a Hess's law problem are to manipulate the equations however you need to in order to get products where you need them and reactants where you need them and the appropriate numbers. Add and subtract the reactants and products. Whatever you did to the reactants and products as far as reversing a reaction or multiplying it through by a certain number, you need to do that to your delta H values. Cancel out what appears on both sides of the equation so that you are finally left with just what you need for products and reactants. And then add up all of your numbers. There are a lot more practice Hess's law problems on the website. I would encourage you to try quite a few for yourselves. I hope this video has been helpful.